Okay, y'all, I just wanted to go over one more example. Well, excuse me, three more examples. So this is the second part of the notes from today over 9.8. It's kind of more dealing with word problems. Like, what does this second derivative even mean? Now, what I want to start with is this observation right here. In fact, I'm going to put it in red because it's important. Y double prime measures the instantaneous rate of change of y prime. Y double prime measures the instantaneous rate of change of y prime. Now, why is that and why can we justify that? Well, notice if I just take off one tick mark, what this is saying is y prime measures the instantaneous rate of change of y, and that's, of course, true, right? So it makes sense that y double prime has the same relationship to y as y prime has to y. So y double prime relates to y prime the same as y prime relates to y. So y double prime measures the instantaneous rate of change of y prime. And in fact, you can go a little bit further. Turns out y triple prime will measure the instantaneous rate of change of y double prime, right? When you derive something, it measures the instantaneous rate of change of the function beforehand. So boom, that is our big observation of the day. Now let me go ahead and translate this equation. This equation is y equals 24x squared minus 4x cubed plus x. That's what y is. And notice it's asking, hey, what is the rate of change of y prime? If it asks you for the rate of change of y, you'd say, well, of course, just take the derivative. 48x minus 12x squared plus 1. And since it gives us a point, we would plug in 1 comma 21, and that would be the rate of change of y at that point. So rate of change of y at that point would be to plug in 1 comma 21 to my derivative, which would just be the same as plugging in the x value of 1. Now, since we're after the rate of change of y prime, that's where we need to get a second derivative. So y double prime in this case is 48 minus 24x, because the plus 1 goes away, it doesn't have a dance partner. Now we're interested in the rate of change of y prime at the point 1 comma 21. So all we do is we plug in 1 to our second derivative, since we're measuring the rate of change of y prime. So we plug in 1 to our second derivative to get 48 minus 24 times 1, which is just 24, and that is our answer. Y double prime measures the instantaneous rate of change of y prime. Now, one particular example that we related was the physics example. So, importantly, if I can spell position right, the derivative of position was velocity. So if this is y, which typically it's denoted s, so I'm actually going to do that. And it's usually a function of time. Its derivative, velocity, is s prime, which we usually call v. Now what happens when we derive velocity? What is the rate of change of velocity? It turns out that's acceleration, which we usually call a of t. And it turns out, like I said, that's the rate of change of velocity. So that would be s double prime, or if you want to, v prime. So you can kind of see that these second derivatives can be layered and kind of combined in different ways, but if you start with position, when you derive it, you get velocity. If you derive position a second time, you get acceleration. So ultimately on the homework, you'll be asked something like this. Hey, a particle travels according to this formula right here, which is the function s of t equals 80 plus 7t plus 0.08 t cubed. where S is in meters and T is in seconds, and it's going to say find the acceleration at T equals 6. Well, that's actually not too bad. First off, let's find the velocity function. So my velocity is just the first derivative, that's just 7 plus, and I guess 0.08 times 3 would be 0.24 t squared. So that ultimately acceleration, which just happens to be my second derivative, well, the derivative of 7 is 0. So ultimately what I'll get is 0.48 times t. Now, since I'm finding my answer, since I'm going to find the acceleration when t equals 6, all I do for a final answer is I say, hey, wait a second. This is just s double prime of 6. Make my handwriting a little bit better. Hey, that's just 0.48 times 6. And I'm literally going to my calculator right now to figure that out. But the main thing that I want you guys to take advantage of and to know is that, hey, given position, if you derive it, you find velocity. And if you derive it a second time, you find acceleration. And the acceleration at the particle at 6 seconds will be equal to 2.88. Now our units for velocity, in this case, will be meters per second. Our units for acceleration will be meters per second squared. So boom, plug in 6 to your answer. But the main point of this problem is the second derivative of position is acceleration because of that relationship. Last but not least, we're going to have some marginal revenue problems here, of course, since this is a business calc class. I'm going to go ahead and copy down the revenue function. The revenue is 70x plus 0.8x squared minus 0.003 x cubed, where x is number of units sold. Now notice the question, it's being a little subtle in its wording. How fast is marginal revenue changing? So we're talking about a rate of change of marginal revenue. Well, in order to get the marginal revenue, remember that we just derived revenue. Okay, so that's not too bad. Let's find R prime. That's just 70 plus 1.6x minus 0.009 x squared. That's our marginal revenue. So if it said, hey, what's the marginal revenue at 10 units? You would plug 10 into this function right here. And bam, that's what it is. Now, since we're finding the rate of change of marginal revenue, what we want is like marginal revenue prime. How does that tie into this section? Well, that's R double prime. The derivative of 70 is 0, doesn't have a dance partner. The derivative of 1.6x is just 1.6. And the derivative of this guy over here will be negative 0.018x, I believe. Therefore, the rate of change of the marginal revenue, which rate of change is derivative, so the derivative of the marginal revenue at 50 units we'll get by just plugging in to this function. So 0.018 times 50 is 0.9, and we're going to do 1.6 minus 0.9, which will give me 0.7 as an answer. So we would say that the marginal revenue is changing at a rate of 0.7. That's how these problems are going to come up in word problems. Okay, so you got to realize that the second derivative describes the rate of change of the first derivative. Similarly, the 99th derivative describes the rate of change of the 98th derivative. It's always describing the rate of change of the one before it. That's why the first derivative described the rate of change of the second derivative. Or the first derivative described the rate of change of the original function. Second derivative describes the rate of change of the first derivative. I know it's confusing. Please go back and review all these problems. Pause on them. Understand why they're asking what they're asking. And other than that, I'll be uploading this stuff. And good luck.